I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. So in our last video, we have discussed about simple harmonic motion. What are the different characteristics of simple harmonic motion? And also we have taken some of the important terms related to simple harmonic motion. And we have discussed two types of simple harmonic oscillator. One by taking one mechanical harmonic oscillator, where we have taken mass connected to a spring, and we have taken electrical harmonic oscillator, where we have taken LC circuit. So where we have considered electrical oscillations in LC circuit, and also we have derived second order differential equations for those two harmonic oscillators. Now today in this video, we are going to discuss about damped harmonic oscillator. So we are going to take what is the possibility for having damped harmonic motion. We'll try to get what are the different forces that are acting on this damped harmonic motion, and we try to get second order differential equation for it. And then by taking solution for that differential equation, we'll try to work out what are the conclusions we can draw from this damped harmonic motion. And also we are going to correlate with day-to-day life where exactly this damped harmonic motion is being used. So continuing with our discussion, as I told you, today we are going to discuss about damped harmonic motion. Now what is damped harmonic motion? So here what you will observe here is, suppose if you take free oscillations, free motion, if you consider free harmonic motion, what you will observe here is this amplitude of vibration, it will keep on going and going. So here amplitude will not decrease with respect to time. But whereas when we are considering damped harmonic motion, suppose I have a body which is executing vibrations. For a body which is executing vibrations, you will observe that amplitude of vibration, it will keep on decreasing slowly. And why it is going to decrease slowly? Because of some resistive frictional force acting on it. So what you will observe here is, suppose again if we go back to our pendulum case, okay, if you go to simple pendulum, or you can have mass connected to a spring. Suppose I have a spring, and to that spring I have connected mass. So here what you will observe here is, once I make this mass, if I take it to suppose if this spring, it has started oscillating. Once I set this particular system into oscillation mode, what you will observe here is, when I am saying it's a damped harmonic motion, you will observe that its amplitude of vibration, it is slowly going to decrease. And why it is going to decrease? Because there is one force acting on it in order to oppose its vibration. That force, it is called as resistive frictional force. And because this force is acting and which is trying to make its amplitude decrease with time, you'll observe that after some time, total vibrations will die out. So such motion which is damped, here dampening of vibrations are slowly decreased and vibrations will die off. So such motion where we have dampening of vibrations due to frictional forces, it is called as damped motion. And you may wonder what are the different frictional forces that are acting on such system. So coming to the different forces, it can be air resistance, or it can be friction, or it can be intermolecular forces where energy is lost in the form of heat or sound. So these are some of the factors in day-to-day life which go for damped harmonic motion. And what you will observe here is, damping, it will be present more or less in almost all oscillatory systems. And one more thing is, one more factor that will result in dampening of oscillations is, suppose if you consider certain fluids, if you keep your system in certain fluids like air or water, what you will observe here is there will be interaction of molecules of the fluid. There will be air resistance. Because of this also vibrations will get die off. They will get damped. And coming to some examples in day-to-day life where we can see this damped harmonic motion. One example, we have our yo-yo, which is played by kids, and of course we have our clock pendulum and also guitar string. So these are some of the examples of damped harmonic oscillators in day-to-day life. Now what we are going to do, we are going to take one example and we are trying to see what are the forces acting on it, and using those forces we'll try to get differential equation for this damped harmonic motion. Now as you can see, this is the example I have selected here today in this case, and what I have taken a spring, and the spring is connected to mass. And this spring and mass system, if you see here, this particular mass, we are going to immerse it in a fluid. So here, as you can see, what is the example we have taken? Here we have taken a mass connected to a spring, and this mass, it is being immersed in liquid. And what this liquid is going to do? This liquid, it is going to exert some frictional force on mass, which will try to dampen its vibrations. So this is the example which we are going to consider here. Now once we have such system, spring mass system, and that spring mass system being immersed in a fluid, we'll try to figure out what are the different forces acting on it and why its vibrations are dampening. So here, as I told you, we are trying to get expression for a differential equation for damped simple harmonic motion. Now if you take damping forces, so here damping system, if I take damping system, so it is subjected to two types of forces. First force is restoring force. So what is happening when I make like spring and mass system to vibrate? If I make my mass displaced from its position, then obviously there is one force acting on it. And what is that force? Restoring force. And we know that this restoring force is proportional to displacement of the mass. And what is the direction of the force? It will be opposite to the direction of displacement. And as we know that force, it is proportional to displacement, and if I try to remove this proportionality sign, I'm introducing one constant K, and of course our constant K, it is called as force constant or spring constant. And how it is defined? It is defined as force per unit distance. So this is one of the force which is acting on our spring mass system. So first is the restoring force, and why we are using this minus sign? Because our force always act in a direction opposite to the displacement. Then next is, what is the second force which is acting on this particular system? Here we have frictional force, and this frictional force, it is exerted by fluid in which we are inserting our mass. So this, because of that frictional force which is exerted by the fluid only, gradually vibrations will die off. And you'll observe that this frictional force, it is proportional to velocity. So, and we know that this velocity, it can be given in terms of displacement as dx by dt. And if I try to, here we have taken this velocity and our frictional force is proportional to velocity. And if I try to remove this proportionality sign, here also I am introducing one constant r. And what is this constant r? It is called as damping constant, or it is also called as frictional force constant. And it is defined as frictional force per unit velocity. And here also we are taking negative sign. Why we are taking negative sign? Because even frictional force direction will be opposite to the velocity. So that's why here we are taking negative sign. So there are two forces acting on the damping system. First one is restoring force, which will try to bring mass to its mean position or equilibrium position, and then frictional force, which will play a role in order to dampen vibrations, and it depends upon the velocity of vibration. And then I'm making use of Newton's second law of motion. And according to Newton's second law of motion, how we can write force? Force is mass into acceleration. And if I try to denote acceleration in terms of displacement, it is second order derivative of displacement. Now if I consider all these three forces, so this force, due to Newton's second law of force, it should try to balance the forces, two forces which are acting on the damping system. Then we end up having our equation like this. So md square x by dt square, it is the force that comes from our Newton's second law, and minus kx, it is our restoring force which is acting on our spring mass system, and minus our dx by dt, it is the frictional force which is trying to dampening the vibrations, amplitude of vibrations of system. And if I take these two forces to the other side, I'll end up having this equation. And then what I'm going to do, I'm going to divide this particular terms with m, mass of the block or mass that is connected to spring. So once we divide, then our second order differential equation, it gets modified like this. So d square x by dt square plus r by m dx by dt plus k by m x is equal to 0. Now I'll try to simplify this second order differential equation further by taking this r by m. I'm denoting this r by m by 2b, and I'm denoting this ratio k by m, spring constant, to the mass as omega square. Then we have a simplified second order differential equation as d square x by dt square plus 2b dx by dt plus omega square x is equal to 0. So here 2b, it is a damping factor, and whereas this omega square, it depends upon our spring factor. So force exerted because of the spring. So this is the second order differential equation for damped harmonic motion. Now next we'll try to find solution for this second order differential equation, and from that solution we are trying to consider three important cases, special cases. Okay, so now we have this second order differential equation. How we can write solution for this equation? Now a solution for the second order differential equation, which is given as d square x by dt square plus 2b dx by dt plus omega square x is equal to 0. This is our second order differential equation. Now for this, I am writing my solution in terms of exponential. We know that solution can be written in terms of sine, cos or exponential. So here displacement is given as a e to the power of alpha t. What is a and what is alpha? Both of them are constants, and of course t is our time. Now what we are going to do, I am going to differentiate this particular equation, and I am going to substitute in our differential equation. So here I have d square x by dt square as well as dx by dt. So I'm going to differentiate this equation once. That will give me dx by dt, and this dx by dt value, it comes out to be a alpha e to the power of alpha t. And if I differentiate this again, this expression again, here we are differentiating our displacement twice, then we end up having a alpha square e to the power of alpha t. Now I'm going to substitute these values of d square x by dt square as well as dx by dt in this particular expression. So what we have in place of d square x by dt square, as I got a alpha square e to the power of alpha t plus 2b is already there in our equation. Then we have dx by dt, which is given by a alpha e to the power of alpha t plus, and then omega square, and we have x displacement, we are defining it as a e to the power of alpha t is equal to 0. Now I am taking out common terms outside. What is our common term? A e to the power of alpha t. Then I end up having here as alpha square plus 2b alpha plus omega square is equal to 0. Now here there are two terms which can be equated to 0. A e to the power of alpha t, it has to be 0, or this term in the bracket, it has to be 0. But I can't take this to be 0. It means that if I take it to be 0, then there is no there's such thing of discussing about displacement in case of damped harmonic motion. So we cannot make this displacement 0. So that's why we have to take this term in the bracket to be 0. And if I try to find roots for this particular equation, so as we know that so here in this case, when we are trying to find roots, so here I got two roots for this equation, and what are those two roots? Minus 2b. So actually minus b plus or minus square root of b square minus 4ac by 2a. This is the formula for the roots of the equation. So if we have our equation as ax square plus bx plus c, if we have this equation, then further its roots, they can be written in this formula. Now, if I try to compare this equation with this equation, so what is my b? B in place of b, I have minus 2b. So in place of b, I am substituting minus 2b. And b square, so b is nothing but 2b. So b square, it will give rise to 4b square. And then 4ac, 4 into what is our a? A is 1. and C is our omega square. So we'll have 4 omega square by 2A. So here A is 1. So we end up like this. And if I try to simplify it further, then my alpha value, it will come out like this. Now it consists of two roots. So one is alpha 1, and how this alpha 1 is given? Minus B plus square root of B square minus omega square. Then alpha 2, it is equal to minus B minus square root of B square minus omega square. So these are the two roots we got, and using these two roots I am going to write solution in this form. So the general solution for second order differential equation associated with damped harmonic motion, it is written as A1. Of course, here I am introducing two constants A1 and A2. A1 exponential alpha 1t plus A2 exponential alpha 2t. What is my alpha 1? Alpha 1 is minus B plus square root of B square minus omega square. What is alpha 2? Minus B minus square root of B square minus omega square. Now I'm going to take this solution and I'm going to consider three important cases. Now here, if you take that expression, so what is our expression? We got x is equal to A1 exponential minus B plus square root of B square minus omega square t, plus it consists of two terms. Then second term is A2 exponential minus B minus square root of B square minus omega square t. So this is how we have defined our displacement. Now there are two important factors in this equation. So what are those two important factors? One is B and other one is omega. Now what I am going to do, depending upon the relative values of B and omega, I am going to consider three important cases. So first case, I am calling it as underdamped motion. What is underdamped motion? For underdamped motion, I am saying that B square value, it has to be less than omega square. So B square is less than omega square. Now we'll try to see what happens. What is B square? B square, here we are talking about dampening factor. Omega square, we are talking about spring constant factor. So if B square is less than omega square, frictional force is less than our restoring force. If effect of frictional force is less than the restoring force, I think we can make out from here only, but we try to first come to conclusion using mathematical expressions. So here, as you can see, here I have square root of B square minus omega square. Now I am taking minus outside, then I end up having square root of minus 1 into omega square minus B square. And we know that square root of minus 1, it is given by I. So here I have this. So finally what you will observe here is this, I can write it as I beta. What is my beta here? Beta is square root of omega square minus B square. And this particular value I am going to substitute in my solution. So if I substitute in the solution, I end up having x is equal to A1 exponential. So in place of this, I am going to write I beta. So here also in place of this, I am going to write I beta. So I'll have it as A1 exponential minus B plus I beta t plus A2 exponential minus B plus I beta into t. Now, what we are going to do here is, now as you can see, here minus bt, it is common in both these terms. So I have taken this e to the power of minus bt outside. Then here I am left with A1 exponential I, so exponential I beta t. Now we know that this, it can be written as cos beta t plus I sin beta t. So in place of this, I am writing like this. Okay. So and similarly here also e to the power of minus bt we have taken outside. So this will be left with A2 cos beta t minus. So here, because here we have minus here. So here minus b minus I beta t. So minus I sin beta t. Now what I am going to do, cos beta t, common terms I am taking outside. So I end up having A1 plus A2 cos beta t plus A1 minus A2 I sin beta t. And now I am introducing two terms. This A1 plus A2, I am calling it as A sin phi. And then A1 minus A2 I am calling it as A cos phi. If I substitute my final equation, it will come as x is equal to A e to the power of minus bt sin of bt plus phi. So this is the equation which we got. Now, what conclusion we can take from this equation? If you consider this new form of displacement, you will observe that this displacement, it consists of this sign factor. And we know that, so what is the expression we got for displacement? A e to the power of minus bt sine of bt plus phi. Now, if you see this expression, what conclusions we are going to make from this expression is very important. Now, we know that sine, it varies between +1 and -1. So, amplitude, so that's why this displacement, you will observe that this displacement also, it varies between plus a e to the power of minus bt or minus a into e to the power of minus bt. And here this e to the power of minus bt, it is called as damping factor. And here what you will observe here is, so we know that time period t, how exactly time period is given? It is given as 2 pi by omega. But what is our omega here in this case? So here omega is, so here it is in the form of, suppose if I have taken this expression, so this I can write it as a sine omega t plus phi. Okay, if I try to compare it, here amplitude, it is given by a e to the power of minus bt, and our omega, it is given by beta. So here, but we know what is beta. Beta is square root of omega square minus b square. So that's why in place of omega, I'm writing 2 pi by square root of omega square minus b square. But actually, you are observing that time period is given like this, usually. But here in our case, when we are taking this damping force to be less than the restoring force, and here we know that omega square is very small, because omega square is very small, then omega square minus b square value will be larger value. If this is larger, then time period, it will be, this time period, it will be more. So you'll observe that this time period will increase. So time period in this case will be higher than our usual time period. So it means that time, there will be much time, or the time taken for the vibrations to damp out will be more. It means that amplitude decreases gradually. So slowly amplitude of vibration decreases, and then it will come back to 0. So such type of motion, it is known as underdamped oscillation. And examples are, of course, when we make our pendulum oscillate in A, then what will happen? Pendulum, it will make to and fro vibrations, and slowly, with respect to time, its vibrations, they are going to die off. And similar case with electrical oscillations in LCR circuit. So this is our first case, underdamped motion. What is underdamped motion? If you take our system, if you make it vibrate, then what you will observe here is its vibrations, they are not going to die off abruptly, suddenly, but slowly. Suppose if I have taken pendulum, so it will start making oscillations to and fro, and slowly its amplitude is going to decrease gradually. Why? Because here time period in such case is higher. So time taken to make one complete oscillation is higher. So amplitude, it is going to decrease gradually. And that particular factor we can see in this particular figure. So here with respect to time, we are trying to make out what is the displacement of the damped harmonic motion. As you can make out, so this amplitude of vibration, it is varying between plus a e to the power of minus bt to minus a e to the power of minus bt. So to and fro motion. So plus value and then minus value. And if you go with respect to time, what is happening to amplitude of vibration? It is decreasing, and slowly its vibrations will die off. So that is nothing but underdamped oscillation. And it occurs when your fractional force is less than your restoring force. Then we are going to consider second case, that is critically damped motion. And what exactly is critically damped motion? And this case is very important case, which has got many applications. In this case, I am taking that let b square is equal to omega square. Let us suppose that b square is equal to omega square. Then coming back to our again equation for displacement. What is the equation for displacement? We have a1 exponential minus b plus square root of b square minus omega square t plus a2 exponential minus b minus square root of b square minus omega square t. This is the expression we got. And because b is equal to omega, so what happens to this term? This term, actually we can say that it is not equal to 0, but this value, it is equal to very, very small value, and that small value we are taking it as h, and this h value, it is tending to 0. So for simplicity's sake, we are assuming that. So we are not taking the square root of b square minus omega square to be 0, but we are taking it to be a very small value. So in place of this, if I substitute h, then my displacement, it gets modified as x is equal to a1 exponential minus b plus ht plus a2 exponential minus b minus ht. Now I am taking common terms outside. What is our common term? E to the power of minus bt. Then I end up having a1 e to the power of ht plus a2 e to the power of minus ht. And if I try to expand e to the power of x, we know how to write e to the power of x1 plus x square plus so on. So here e to the power of ht can be written as 1 plus ht plus so on, and e to the power of minus ht we can expand it as 1 minus ht plus so on. And what I am doing here is I am neglecting higher powers of h. So we are neglecting higher powers of h because we know that h is very, very small, and its higher powers values will also be very small. So for simplicity's sake, we are neglecting higher terms. So we end up having this expression. Here we have neglected higher powers. And if we rearrange the terms, then we end up having this as e to the power of minus bt into a1 plus a2 plus a1 minus a2 ht. Now I am introducing two parameters. I am calling this a1 plus a2 as p, and I am calling this a1 minus a2 h as q. So now this is the expression for displacement. So this expression is completely different from the expression we got for underdamped oscillation. Their sign factor is there, and because of that sign factor, you will observe that amplitude are decreasing gradually. But we'll see what conclusion we can draw from this displacement. So if I take this expression, what is the expression we got? E to the power of minus bt into p plus qt. Of course, where p is r, a1 plus a2, and q is a1 minus a2 into h. Now, if you see this expression for displacement, what you will observe here is there are two factors. This is first term and this is second term. And what you will observe here is when you set a particular body into motion, and in that case, when your restoring force is equal to frictional force, because we have taken b square equal to omega square. So forces are getting balanced. So what you will observe here is displacement of that particular body first increases. So displacement, it is directly proportional with respect to time. And why it increases? Because of this factor p plus qt. But at the same time, we have one dampening factor. What is the dampening factor? E to the power of minus bt. And what this dampening factor it will do, even though first displacement has increased, then because of this dampening factor, displacement, it starts decreasing and displacement reduces to 0 as time increases. So first your displacement shoots, and after shooting, then what you will observe here is what happens to the oscillation? Oscillations will suddenly reduce to 0. So here body comes back to its equilibrium position more quickly. This type of motion is called critically damped motion. In order to understand it better, we'll try to take one example. Suppose if you take our voltmeter, you have connected voltmeter in our circuit. Suppose I'm just in that circuit around 6 volts is being circulated. Then what you will observe in voltmeter, that needle in the voltmeter first it will get displaced. Okay, so it will first increases that needle, it goes to the position of 6 volts, and once it goes to 6 volts, suddenly it will stop its oscillation. So it will reach to stable position suddenly. So what is happening there? Because of dampening factor e to the power of minus bt, once it goes to its position, its oscillations are dampening very fast. So that's why, as you can see, the pointer first moves to correct position and then comes to rest without oscillating. So what is our critical damping? It's the condition in which dampening of an oscillator returns this particular dampening of oscillator results in returning as quickly as possible to its equilibrium position. So first, the critically damped system, it will overshoot the equilibrium position, but if it does, it will do so only once. So here we can try to explain it using this particular graph. As you can see, first displacement is there with respect to time. Then what happens? Suddenly it will come to rest. Its displacement reduces to 0 without oscillating. So this is the case of critically damped motion. Then coming to third case. So our third case is over-damped motion. So in case of over-damped motion, what we are taking our B square to be greater than omega square. It means that frictional force effect is more on the body compared to its restoring force effect. So obviously we can make out what happens if frictional force is more. If frictional force is more, it means that your system, its vibrations, they'll try to die off very fast. So here we'll try to explain it in terms of this factor. As you know, because B square is greater than omega square, so this particular value, it will be real, and this value, it will be less than B. This value, it will be less than B because B square is greater than omega square. Okay, so this value, it will be less than B. So if it is less than B, then what you will observe here is already we have minus B plus value which is less than B. It means that this value is negative. And also minus B minus value which is less than B. So this value is also negative. It means that our displacement, it consists of two terms which are negative terms. And because we have expression for displacement as A1 exponential minus B plus square root of B square minus omega square T plus A2 exponential minus B minus square root of B square minus omega square T. So now these are negative terms. Okay, so these are negative values. So it means that our displacement, it consists of two terms which are exponentially decreasing. So what you will observe here is displacement, whatever two terms are there, both of them, they die off exponentially to 0 without performing any oscillation. So one best example is what happens if you make your pendulum oscillate in thick oil. So thick oil, it will exert very high frictional force on that pendulum. So that pendulum, it won't oscillate at all. It won't perform any oscillations at all. So that we can better understand using this figure. So what is happening to over-damped system? So here you will observe that oscillations are dying off very fast. So, and one point what we have to understand here is larger the damping, the longer the time to decay from its initial disturbance. Now, if you put all these three cases together, we can consider in this figure. As you can see, this is the case, okay, where we have taken B square to be less than omega square. What do you mean by B square less than omega square? When frictional force effect is less. So in that case, the vibration of system, slowly they'll die off. They'll take time for the vibrations to die off to 0. Then we have gone for critically damped oscillation. In critically damped oscillation, you will observe that displacement, first it will increase, and suddenly it will come to its stable oscillation, stable position without oscillating. And in case of strong damping, there is no oscillation at all. Even though if you take your body, if you displace your pendulum from its equilibrium position, because of very high frictional force, it won't perform any oscillations at all. That is known as the strong damping. So one very good example, in order to explain this, in order to understand these three cases in day-to-day life, I have taken an example of a door. And to that door, we have a spring, and that spring helps us to close the door. So what you will observe here is, now we can try to explain three types of damping. Now what you will observe here is, suppose if you say that your door is undamped. So there is no dampening. It means that your door, it will keep on swinging back and forth. So it will keep on moving back and forth. It means that its vibrations are undamped. And if you say that its vibrations are underdamped, then what you will observe here is slowly it will swing, and then what will happen after some time, it will come to a stop. Whereas it won't come to a stop in undamped vibration. Now, to better understand critically damped vibration. So here, what you will observe here is once you open the door and leave it, then what will happen? It will return to closed as quickly as possible without oscillating. Whereas if you go for O-damped oscillation, if I open the door, then it will be open only. That is O-damped. In critically damped situation, if I have opened the door, then what happens to door? It will go into the closed position very quickly without oscillating. Whereas in underdamping, what happens to the door? It will swing back and forth for some time and then it comes to rest. So this is one good example to understand these three cases of underdamped, O-damped as well as critically damped situations. So with this, we are going to conclude our session today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.